Let's look at detailed descriptions of each of these major components. The CSI camera with telephoto lens, which one do I use? What is that? A little bit about the Pi 3 Model D and how it's assembled into a unit that you see here. And a lot more information about the Bushnell sports radar, what was involved in hacking the hardware. I'll show waveforms of the outputs, simple outputs that are needed to be married over to the Pi, and describe the very, very simple circuits that were needed to accomplish this. Finally, or not so finally, I will describe in somewhat extensive detail the executable that I wrote in order to run the show here. And then finally, I'll show and describe what is involved with setup, operation, and comment on some of the analysis that one could do on the images that result from all of this. Okay, so let's look at the camera with its mounted lens. This unit was purchased from China. I think it was maybe about $35. It's set up for the Raspberry Pi. Why I bought this unit is because it has a lens which has a CS mount on it, which then allowed me to replace the lens with the one that I wanted. This has the IR filter, 5 megapixels. All of this numbers that you may be familiar with if you are a Raspberry Pi camera person. The only thing remarkable about it is the replaceable CS mount for lenses. Also available in China from Chinese vendors at a very reasonable price, I think it was around $30 or so, is this telephoto lens. This particular type of lens is commonly used for CCTV applications, and it actually is quite powerful, has a significant range from wide angle to telephoto. Now all of this was assembled as shown. Let's just start with a nice solid plastic base. Everything is screwed down into this base. The lens needs to be, which is the lens with camera, is somewhat heavy and needs to be mounted in a sturdy fashion. This is shown in the picture how this was done. The Pi with its plastic case is screwed down to the solid plastic base. If you take the Pi plastic case apart and the Pi itself, you'll see that you can find some rooms on the bottom to put a few screws in, and everything is threaded into the solid plastic base. And there also you see the GPIO breakout cable. Now let's talk a bit about the Bushnell sports radar and its disassembly. This was the unit I started with. I had it for a number of years, and I ended up purchasing another newer unit after I fooled around with this unit, and actually the implementation you see in the pictures here are the new unit, but they're identical. 4 screws, or rather 4 screws on the body and 4 screws on the handle uh, keep the two halves together, and removing these allows you to take off the cover portion, and you'll see mounted inside everything. In particular, the gun diode assembly is mounted at the base of a large metal horn antenna. You'll see the battery compartment, which normally holds 2 C cells, and to the rear of the unit is all of the circuitry, which I'll describe now. In particular, the display, LCD display, is mounted to what I'll call the main board. If you remove the main board along with the display, it exposes the gun diode assembly. And the gun diode assembly is mounted, as I said, to the back of the horn antenna. But also you'll see a circuit board with electronics. Essentially, the electronics are there to do preamplification and to provide a boost converter to convert the 3.2 volts from the batteries to the 5 volts required by the gun diode. Close-up of where the gun diode attaches. It attaches to a preamp board. The gun diode is a 3-terminal device, very simple. There's a ground connection. There's the DC input, which is essentially the 5 volts, which gets the diode oscillating, and inside that assembly is the mixer diode, whose output is simply the Doppler frequencies. Now for a bit of description on the main board, because this is where one gets the signals necessary to marry over to the inputs on the Pi board. There's an audio output and a comp output. Essentially, the audio output are the Doppler frequencies provided by the preamp board from the gun diode mixer diode. This audio signal routes to the input of an op-amp up in the corner, and that op-amp is configured as a comparator, and I think that's why they label its output COMP. And if you trace that output, it runs down to the TI processor and is attached to one of the pins on the TI processor. If you blow up things a little bit more, you can see that the trace how the audio output routes to the negative input on the LMV331 op-amp comparator, and the output pin runs over to the COMP connection. We need now to look at the waveforms. Waveforms on the audio output and waveform on the comparator output. This is seen here at about a 500 microsecond per division enlargement on the time base. The yellow trace is the audio output, the purple trace is the comparator output. One sees that the audio output rides on a 1.6 volt DC. There is a ripple on this DC output of about a few tenths of volts. The ripple produces output pulses on a comparator um, output as seen here. You could see they are of variable occurrence in time, and if one measures the period of some of these pulses, you'll see it just jumps around uh, according to the ripple that is producing these pulses. Now when a vehicle approaches and the Doppler signal out of the mixer is of moderate amplitude, one begins to see the audio output providing a clear audio signal of a fixed period, and that fixed period represents the speed. The comparator output becomes very regular. One sees the square wave pulses there in purple. And then going on for a strong Doppler signal, the audio output will saturate. You'll see it'll clamp at about 2.7 volts DC and oscillate between 0 volts and 2.7 volts. The comparator output has a nice clean square wave signal, the period of which represents the speed. The comparator output clamps between 0 and 3.2 volts. Now if we look at the big picture, change the time base to 200 milliseconds per division. We'll just look at the audio output only. A car coming down the street ends up looking like this. A pulse of Doppler frequencies begins. The audio output saturates. Towards the end, the strength of the signal decreases, the pulse of frequencies decrease back to DC level. Here's an example where two cars passed in succession, and this gets us to what the problem is. With no Doppler signal present, the ripple produces a comparator output with pulses. Although this output is fed directly to the TI processor, that processor somehow distinguishes these ripple pulses from those of the Doppler pulses. I attempted to do this algorithmically in the executable running on the Pi, and after lots of attempts, I did not succeed to do what apparently the TI processor is doing. So rather than continue to go down that path, I decided to implement a straightforward hardware solution by providing an auxiliary circuit consisting of a simple op-amp comparator, just like in the on the main board here. But this comparator on the reference input has a adjustable reference level. So with this, it's a very simple matter of adjusting the reference level so that the DC level with its ripple is completely cut off. As a result, the output of this comparator consists only of pulses generated by Doppler signals. And when no car is present, there's just smooth DC with no ripple. How this was done was very simple. Take any old simple op-amp. This was an older Micrel 7101 SOT23-5. Solder up on any old circuit board that you can come up with. It's very simple. 3 inputs in and 2 outputs out. So as you notice, we're talking about the simple circuits now, and the only other simple circuit is the 5 volt to 3.3 volt converter. Uh, this was a very simple uh, part number that you could get from DigiKey or Mouser or from anywhere, and the output has a tantalum 33 microfarad. Uh, this circuit replaces the batteries. As far as a 5 volt wall charger, most any will work. Best to use perhaps one with at least the 800 milliampere output or greater. Here is the on-off relay board, and I'm not going to go into any detail on this because it has not been used, and has some level of complexity because I adapted a latching relay, and to operate a latching relay one requires an H bridge, and since the relay is 3.3 volts and the or rather the yes, the relay is 3.3 volts in this case, and the power to this is 5 volts. One needed a level shifter.